I will be covering. I am planning to cover the issue on the expected value of a dice roll. There should be a question. We should ask a question in that scenario. Then it would be meaningful. The expected value of 3.5 will become meaningful in that occasion. After that, I will be talking about the skewness and kurtosis, which I will be covering this briefly. And after that, we will be talking about the distribution, joint probability, marginal probability, conditional probabilities, these topics. And if there's time, I'm planning also. I might cover also the other topics. I'm not sure about that. Let's start with the expected value of a dice roll. The question. The nuance here is if you earn points the phase which you have received, then the expected value of 3.5 becomes meaningful. Let's assume a scenario. Let's say that we are rolling a dice, and every time I roll, I'm earning the point which is written on the face. So let's say I roll the dice and I get three. Let's say three. I'm sorry. Let's say four. When I get three, I earn 3 points. When I get four, I earn 4 points. So you mean earning is important. This nuance in here is this. If I earn these points, and then the expected value becomes much more meaningful. Now we can talk about this because now the ranking between these numbers becomes meaningful. In this situation, when our expected value for a dice having 6 faces is 2.5. Now we can expect to earn 3.5 points from a dice roll. This is the nuance here. And this in this situation, our approach to expected value makes sense. And let's talk about the skewness and kurtosis. I think these measures uh, the our shape of our distribution actually. Skewness, how sorry. How symmetric our distribution is, and it measures how symmetric or asymmetric our distribution is. If it is bigger than zero, I guess it leans towards the right. If it's smaller than the zero, it leans towards the left. And as you remember, this is a normal distribution, right? Let's say this is a normal distribution, and let's say this is symmetric, then our skewness is zero. And if it's something like that, then our skewness is smaller than zero. Okay. If our distribution is like that, then skewness is bigger than zero. So skewness actually is the third moment of the distribution, and there's a formula for that, and it is like that. I mean, I did not. Sorry, I didn't use skewness or kurtosis for a long time, and actually, this is this is called the third moment for a random variable, and the cube of the standard deviation, and this is the expected value of spreadness of our, let's say, random variable, and it's a different type of a variance, but not the variance, of course. And we are measuring by this. By this, this is how you measure. How you measure. I mean, this is acceptance, in my opinion. You can measure in different ways, but I guess this is the most efficient way to measure the skewness. And kurtosis is how thin your tails are. Measures how thin your tails are. Or, you know, let's say, you know, I'm going to be drawing to, I'm going to draw the coordinate in this time. You know, so, whoop, and the other one is here, and it's like, whoop. I'm not, yeah, it's not very good drawing. Let's draw it again. Oh my god. And let's say it's like that. So this is tails are much more thick in here compared to this. So this kurtosis and this kurtosis, let's say it has value of alpha. Let's say it's value of beta. So because it is thicker than this, so we are saying that beta is bigger than alpha. So this kurtosis is bigger than them, and also the calculation for this is formula for the calculation of this is like that. And why is important? As far as I remember, the values of skewness and kurtosis of north, I guess standard normal distribution, it was 0 and 3. So if you know these values and if you calculate your distributions, this kurtosis and skewness values, you might think that you might calculate and estimate how normally distributed, how close to normal distribution to your distribution, how your distribution is close to normal distribution. You can measure that and you can develop an idea and an opinion about for this. This is are important because of that. And the joint distribution. So it's important. And joint probability, sorry. And standardized random variables. This is another thing we will be covering here. Standardized random variables actually is important. You know how to standardize random to standardized random variables. How random variable. The aim is here making your mean and variance to equal to one and 0 and 1. So you have a random variable, and let's say it has mean x and variance equal to y. So aim of this process is making your random variables mean and variance to equal to 0 and 1. So after the application of this process, your mean becomes 0 and your variance becomes 1. So how do you do that? So actually, this is a formula for that. So you subtract mean, you know, you let's say, let's say, oh, sorry. So let's say you have y, and you subtract. So you subtract your mean and divide to standard deviation, not the variance. So let's say that we have 3, 4, 5, 1, 9, I don't know, 12. So our mean is 3, 1, 12, 24, 34 over 1, 2, 3, 4, 5, 6. And our I don't want to calculate the variances right now. Let's say we have variance equal to, what is it? I don't know. Let's say 7. So how do you standardize your random variables? You will subtract 3 from you will subtract your mean, yeah, I mean mean from each one and divide the square root of variance. And you will do this every single number. You will do this for every single number, and blah 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 to until the rest until the last one. So why it's important? Actually, it makes things easier to calculate. Having zero mean and one variance is it makes things much more easy to calculate. So we are standardizing our random variables by that. Also, I guess it helps. Also, it helps us to get rid of the units. Yeah, I mean, it's important in the event of calculation and mathematics. So your value becomes unitless, and which, by the way, you can. I assume you can talk. Uh, so you make your assumptions more. How do we say? More generally. I don't know if it's a proper terminology for this occasion. But let's talk about the joint distribution and marginal distribution and conditional distribution. These are important. Actually, conditional distribution is used in the OLS in regressions. It's important. Every time I say joint conditional distribution, arch, the topic of arch in the econometrics comes to my mind. Autoregression, autoregressive conditional heteroscedasticity. And we will be, yeah, like we said, we will talk about the joint distribution. So you have multiple random variables. Well, but let's talk about in the case of two random variables. So you have x and y. These are two random variables. and their probabilities are also different. Actually, I'm going to be using the example of this table. Okay, and we will talk about this here right now. So we have situation a equals 1 and a equals 0 and a equals 1, and we have m equals 0, m equals 1, m equals 2, 3, and 4, and 4. It's 3, m equals 4. Okay, so these are the probabilities, you know. So these are the probabilities. Okay, so joint distribution is, I'm going to be talking about the written things on this book, and this is the probability that the random variables simultaneously take on certain values. So in this situation, A is we have if having we are have a network, and A equals 0 means we have all the network, and A equals 1 means we have new network. And M's are the number of times the failure of the failure of times of failure. Okay, so so when we say that probability of A equals 0 and M equals 2 means that when we using old network and having two failures, what is the probability of having two failures in an old network is 0.05. Okay, so these two occasions happens at the same time simultaneously. So for example, probability of having new network and having four times failure, and it's equal to 0.00. I mean, so this is it. So this is joint distribution. The probability of having how can we say, probability of having multiple occasions it's simultaneously. So marginal probability distribution is kind of a different. So we have it is marginal one is, I will be talking it right here. Marginal distribution is, we can describe it like It's actually says here that it's another random, it's another name for the its probability distribution, which means I mean we can represent it like the probability of having m equals zero. What is it? When we sum this up, 0.8, right? When we sum this up, I mean 0.01, I guess. So you have a you have multiple occasions happen at same simultaneously. However, you only take care of. I mean, you only consider the, only one occasion. So we are only considering about the having zero failures, regardless of the status of the network. I mean, we don't care about the network situation. It can be old network or new network. We don't care about it. We only care about the having zero or one or two failures. When we say that m equals zero, I have m equal probably m equals zero is equal to 0.8. So in this situation, our probability of having no failure is 0.8, so 80%, we might say another way. For example, what is our probability of having old network? It's another thing. We are summing these things up when we want to calculate this, and we can sum it up. I don't know. Let's do it. I'm not gonna be lazy this time. 0.405 if I summed those up correctly. I guess I did. And like I said, so having an old network, probability of having an old network is 0.405, 405. So the marginal distribution and joint distributions are this, but there's also a conditional distribution, which is important. And the conditional distribution of a random variable is, by the way, we when we know the probability values, the conditional distribution of this is we are fixing one of the occasions. I mean, you know, let's talk about it. When we have old network and having one failure, when we consider the probability of happening this occasion is, we have 0. What did you say? 0.065. However, conditional distribution is kind of a different. Like how? We will be talking about this soon. So, in the event of this, I'm sorry, you know, it's written like, by the way, like that's a probability of m and a equals 0. Okay. So, how do we do this? I mean, um, 0 at 8, 0. So, we have a universe. Let's consider the first topics. When we talk about the probability, we have a universe, and in this universe, we have our probabilities. In this situation, our universe is here. Okay. Oh my God, it's very big square, a circle. Our universe is here, but when we talk about it, in the condition of having old failure or old network. I'm sorry. Huh. Okay. So our universe becomes this. So we are only considering about this. So our new universe is here. So we have different probabilities, which is mean. So let's say that we want to calculate probability of having m equals 0 to a equals 0. So which means, so this means is we can interpret it like that. When we have old network, in the having old network, we have a universe only in the have in the only we have only have old network. What is our probability of having zero failures in this universe? So how do we calculate this? So we are summing all these probabilities. So our universe's probabilities, I guess we summed it up 4 or 5. It becomes like that, and we summed it up by this value, and we divide it by this value. So it comes to it's calculated it's approximately 0.70, I guess. Oh my god! I hope I summed those up properly. If not, I will be ashamed. Oh my god, it says 0.60. Oh my god, 0.5. I'm sorry. It makes zero point 0.5. So, yeah. So it makes. So I summed that up wrong. I'm sorry. I made a miscalculation. So, our probability becomes 70%. So what do we mean by that? So we mean that if we only allowed to use alt network, and if in this situation we have 70% likely to having zero failures, we can interpret it like this in these situations. So the conditional probability is this, and also the another topic is conditional expectation. So how do we calculate it? So we are taking actually expected value in these situations. So what do? We calculate every cos expected value of conditional probability of every situations. How do we do that? So and so I'm going to write the formula also. Probability of m equals 1 and a equals 0 is equal to probability of m equals 0 and a equals 0 divided by probability of a equals 0. Okay, I mean, we are changing the universe actually. We are changing the dimension. Maybe we think like that. So uh, expectations. So this is 0.70. This becomes 0.130. 0.70, 0.130. This becomes zero point 0.1. This becomes 0.05. And this becomes 0.02. And. So how do you calculate the expected values? By just our formulas. We are calculating the random variable. We are multiplying and our random variables by its probability values, and there we are summing it up, and we find the how many times to fail our network. So I guess it's calculated by here. So the result is 0.56. So if we use old network, we expect it to fail 0.56 times. And you, these are actually kind of fundamental and important topics also in the, I guess, in probability theory, and also in econometrics and the other things. And we will be also talking about the law of iterated expectations. Why it's important? Because it's using the expected values and the expected value of an expected value and blah blah blah. It makes things much more easier to calculate, which is why it's important. And now we will be talking about this. Now, by the way, we are using modern programs nowadays, so we are not calculating this by hand. I'm also not going to be probably calculate this by hand. However, I don't know. I feel satisfied when I do this, not depending only the computer and not guided by the computer. Makes me feel good. And so the law of iterated expectations is basically it's here. What do we mean by that? So if you take an expected value of your coin, your conditional expected value, you will get the marginal expected value of your random variable. So basically, the law says that. So law of iterated expectations is kind of like that. Why it's important? We can manipulate it by different things, by these and other situations. Mm, for example, in this here, it used three random variables. Let's say that. So we have three random variables x, y, z. So our ay is equal to our expected value of y conditioned to x and z. And okay, okay. Uh, and okay. So these are the things which which we have covered. So the next topic we are going to be talking about is conditional variance. So conditional variance is also kind of a similar thing to conditional expectation. So you are also calculating your variance in the event of x having a value. Let's I'm going to be talking by the core formula here. So in the event of having we have x equal to x, and how do we calculate our variance of y? So it's kind of the same thing. Expected to be, I mean, no, sum of from e1 to k I minus expected value of y times probability y uh, e x equal x. So this is our mean. I mean the expected value, not the mean. So, yeah, this is our mean or expected value in the new scenario, and the probability of our conditional probability. So we change the universe. We develop another approach in this situation. So we are only considering the having old network, for example. We only consider we only have old network. We cannot have any new network. So the other thing is Bayes rule. Actually, it's a similar thing of it's similar to conditional expectation value. I assume or not, or maybe it's about the independence actually. No. Sorry. So probability of y equals y in the event of x having x is equal to probability of x having x in the event of y having y of probability of y equals y times divided by probability of x having x. So actually, we are manipulating the this is Bayes rule, by the way, Bayes rule. Why it's important? We are manipulating the conditional situation. So we are reversing the conditional. How do we say probabilities? So what was our conditional probability of basically in the event of probability of y is equal to probability of uh, x having x in the I'm sorry I our our conditional probability formula is here. It was like this, right? Our probability y equals y, right? It was like that, right? Now we turn this into this. But how? This is important question, and I don't know how actually. Let's try to solve it again. When I started first thing, we maybe use law of iterated expectations, but I'm not sure. So this is EY actually, probably of nah, or is it? Nah, it's probability, not the expectation. So how do we do that? Let's probability of joint probability is this, right? Okay. Now let's write this. Okay, we can write it the same things by different conditionalities, right? So this is actually same. These are actually same. So we are going to make equal these equal equations By using these equations, we will find the base rule. So probability of y equals y in the of event or x equals x equal to probability of x equal x in the event of y equals y times probability of y equals y. So we are going to divide this and here probability of x equals x. I mean, for simplicity, I will be writing all of these things. So the idea here is we can represent joint probability with using two different conditional probabilities. So in this situation, we conditioned our situation by the value of y. In here, we conditioned our situation by in the event of uh, x. So these are actually the same joint distributions, the same occasions happening at the same time. So we are going to make these equal. So these equations should be equal to each other. So how this is how we derive base rule. Uh, so if we divide it, the probability of x equal to x, our to by the way, these are capital X. I'm not. It might not be clear, but these are capital. So our formula for the base rule comes like that. Okay. Oh, I'm glad. I just solved it. Maybe I solved it by first before, but I forgot it. So the situation of independence is like this. So if our conditional probability is equal to our marginal probability, then we say that our events are independent. If we use it, if we represent this by the mathematical terminology, the event of probability y equals y is equal to probability of y equals y in the event of x equal to x. What do we mean by that? Actually, our probability does not affected by the situation of x's. So it doesn't matter what is our how x behaves in the event of the behavior of x does not affect our behavior of y, which is why we say that our random variables are independent because the probabilities does not change, so it does mean that these are not affecting each other. And uh, the joint probability is calculated by how? By multiplying the probabilities of these two events. So the probability of, let's say, x equal to x, and let's assume that our events are independent. Let's use this formula. So probability of x equal to x in the event of probability y equals y, what will be our probability if they are independent? You know, probability if x equals x is equal to probability of x equal to x in the event of y equals y, right? So this one becomes this one. So probability of x equal to x times probability of y equals y. So by multiplying the values of the probabilities, we calculate our joint probabilities. But we can only use these probabilities in the event of independence. If there is no independence, then we cannot calculate our joint probability with this way, by this way. So the next topics which we'll be covering is covariance and correlation. There are also formulas for that. I will not be covering that. However, covariance and correlation, if we talk about briefly, and maybe we can cover it up in the next chapter, much more detail if it's needed. I don't know, maybe. Covariance is the covariance shows us the direction of relation between two variables. If variables are independent, the linear, by the way, linear, it measures linear dependency of the way of dependence. There is a negative uh, relationship or positive relationship. Which what do we mean by that? For example, uh, if our covariance have negative value, we say that mm, if our x is increasing, y is decreasing, or x is decreasing, y is increasing. In the case of having negative covariance value, our relationship is negative relationship. However, if we have positive covariance value, that means our relationship is positive relationship, which is while x is increasing, y is also increase, uh, or while x is decreasing, y, our random variable y, also is decreasing. Uh, However, the note should be taken here is the value of, or the magnitude of the covariance is not important. It does not say anything about how they are affecting each other, how well they are moving. Uh, if we want to calculate or if we want to measure the magnitude of this relationship, I mean, how strongly affect they each other, or how weakly affect each other, we calculate the correlation values. If correlation values take values between, I guess, negative 1 to 1 or 0 to 1. I'm not sure, by the way. I'm sorry, yeah, yeah. It takes between negative 1 minus 1 to 1 plus 1. However, covariance takes values from negative infinity to positive infinity. So these are the topics we have covered today. Thank you for listening. Uh, I hope I was brief. Thank you very much. Have a good day.